My name. Assalamu alaikum. Very good morning, ladies and gentlemen, and dear students. So I'll be talking about, rather, we will be discussing the physics of electron beams. And after yesterday's discussion, everyone would like to have it their own radar, perhaps. But it comes at a price. We should know the actual physics which is behind those devices. And today I'll try to give you an overview of what actually the beam physics is. And electron physics is basically a very short part of the very broad range of charged particles interacting with electric, magnetic, and electromagnetic fields. So it's just an overview. You're welcome, most welcome to study more. Perhaps you have already done it, but I'm Kashif. As you know, I'm currently serving as a principal scientist and group lead for the electron beam generation, transport, and diagnostics group. Whatever I'll present, it is, of course, contributed by my very respected colleagues and my students. So let's begin. This is what we have in our laboratory. It's just a test bench. And basically, our aim of this discussion today should be that we should be having a flavor of the electron guns. And those electron guns have very specific beams. When I say beams, it has a very specific and disciplined definition in physics. We'll come to that point later. And our aim is to have a gun which can be used as a device for the vacuum amplifiers. And this has some certain characteristics. For example, it should have very high current, the beam current. It should be operating in lower transverse emittance mode. Transverse emittance is a very significant characteristic of any charged particle source. When it comes to electron guns, we say that it should be collimated and the beams should go in parallel. For example, if I want to have a route from this side, I should be very slim to have a transportation from this point to the other. So this guy we will discuss in detail in transverse beam dynamics. And it should be able to generate high power when it comes to in contact with electromagnetic seeds or radiations. So this is our aim. We will come to this discussion tomorrow. You should be able to have a flavor how these curves, how these electrodes are designed. And then we will go through a detailed experimental discussion. If you have a gun, what are the characteristics that you need to characterize before this gun can be put to an actual experiment? By the way, you are welcome to interrupt me. I may not be able to answer all of your questions, but yeah, we can discuss. So all of this needs some background knowledge. And any discussion, should start with the Maxwell's equations. Yeah. And then we will discuss about the Maxwell's equations, the wave equation, and we will try to find out the way where Maxwell's equations can be used to devise a principle that is basically governing klystrons, magnetrons, gyrotrons, or any other vacuum device. So we will discuss in bit detail the electrons' motion in static field, in magnetic field, in electric and magnetic field, and what if the fields are time varying. So every characteristic every scenario has its own flavor. And then we will try to find out we will try to define the beam in trace space and phase space. I hope you are familiar with it. This, when I say trace space or phase space, it means that it is position and momentum that is taken into account. And this will bring us to a perfect definition, or the physicist definition on the law of physicists for beam. And then we have transverse and longitudinal beam dynamics through some of these devices. I cannot cover all these in a very short period of time. I've given two examples part of these discussions. And
trace and phase, are they using synonyms?
no, it's more or less similar, yeah. Because trace is slope, and when we call when we take into account the momentum into account, then it's a phase space, yes. Excuse me. And then I will give you a flavor of the electron optics. Optics is very necessary when you want to transport the beam from one point to the other. And we will try to develop a MATLAB program for it. And I hope this example will give you the mathematical insight of this problem. Okay. Tomorrow, I hope these things will give us enough background to grab and digest what we are going to discuss tomorrow. We'll discuss the electron sources themselves. We'll try to devise a source as required by the end user. Remember that the end user is your client, and you have to design a electron gun, electron source that fits the bill. Okay, for mathematical point of view, we use paraxial ray approximations. People, there are papers in early 1940s by Pierce and Dome from MIT, I guess. They have devised Pierce guns. Maybe you're familiar with it. And the geometry of this gun has some shortcomings. The paraxial ray basically takes into account the very important factor, that is the low emittance, yet it has a character of transporting very high charges. Okay, when I say high charges, it means that it should be able to generate high powers. And then we will switch to the sources of those high currents. Those high currents come nowadays using we use dispenser cathodes. Earlier, thoriated tungstens were used, but people now use flash from silk, of course, and field emission, of course. So I will be concentrating on thermionic emission. So that thermionic emission can be very easily understood using Child-Langmuir's law. And we will try to have some flavor in CST, particle and cell simulations, so that we can understand how they actually operate. And at the end, I would like to share some of our practical aspects that we faced during the fabrication. And of course, I have some other examples as well. And at the end, one should be able to analyze an accidental scenario. I will share with you some accident, and you should be able to analyze that, what went wrong with that gun. So maybe it's a homework. It's a school, of course. So, okay, it's not working. The pointer. Pointer. Is this one? No, the slides. You need to click on this time.
Hocam Zoom'a girdiniz ya ondan da. Just click on the PDF.
We have to say every test. Okay, thank you. Okay. Yeah. So I can talk to you in English. You can talk to me in English. I don't know Turkish. But what if we want to talk to a particle? Particle understands two languages. One is the electric field, and the other is the magnet. So these are the two languages that we can use to communicate with a particle. And when I say particle, it is electron nowadays. So when a particle is at rest, the only language it has is electric field. When it starts moving, it's a sort of review, of course. The electric field is sort of reoriented, and another character comes into play, and that character is the magnetic. The magnetic field is usually curled around the source, the charge, and the magnetic electric field is sort of squeezed. It's a donut shape or a tire. So in fact, the interaction of electric field, the electron charges, is possible only through electric and magnetic field. So this is the basics of the electromagnetism. Okay. Why we choose electrons for our purpose? We know that the electrons have a very high charge to mass ratio, and when they are accelerated and put to retarding force, or if the course is changed, the velocity vector is changed, they are actually radiating radiations, and it's easy to have radiations from electrons. By the way, you're all familiar with the synchrotron radiation, so it's a sort of a parasitic thing, but in fact, it is what electrons can generate for us. So the same character is useful when we talk about the oscillators and amplifiers. That is the topic of this school. Okay. Review of the Maxwell's equation. By the way, I have tried to make cartoons for the Maxwell's equations. It's very hard to communicate when we talk. We use only equations, but let's see if the cartoons work. So suppose we have a collection of charges, then someone bringing a test charge nearby can smell the electric field is coming out, the diverging out thing. So it's the first law, the Gauss law, of course. And for example, if you have a surface area and some magnetic field flux is going through it, then it should be the net flux should be zero. So there are no monopoles. You cannot have monopoles. So basically, these are static fields. So static, electric, and magnetic fields, they have a very peculiar character that they can exist independently. I mean, you can have electric field and magnetic field, provided they're not time varying. They should be existing independent of one another. For example, we use this thing in electron guns. Okay, electron guns are usually DC or pulsed operated, and there we always apply some electric field and some magnets. Of course, we will use it next time. But the magnets, you don't have to, for example, in case of permanent magnets, you don't need to have changing magnetic electric field. Whereas the other two cases are different. If we have a time varying magnetic field, then a curled electric field is generated. This curl operator. And similarly, if you have a density of charges, J, the density of charges is moving, has a character velocity. This J is basically the current density. It is moving. The current is moving, and the electric field is time varying. Then we can have a curled magnetic field around that area. This is very different from the static field. In fact, there's this famous saying that one is the other. Wherever you have magnetic field time varying, you always have electric field. Similarly, wherever you have electric field, which is time varying, you always get magnetic field. So one is the other. They are coupled. Naturally, they are coupled. Okay? So far so good, I guess. By the way, Maxwell was a genius, perhaps. And these are the most influential equations of all time. And then some mathematics is carried out. You can say that the electric field vector and the magnetic field vector, they are orthogonal in free space. They can exist at some point where there is no charge as such, but charge is sitting somewhere else. The origin is, of course, charge, we know it. And these waves are moving with the velocity of light. So basically, we're gathering the tools. We remember that our charge understands electric field and magnetic field. So we are hunting the sources of electric and magnetic field.
Kashif, may I ask you a question?
So.
Why the electric field and the magnetic field have the same phase?
Let me come to this.
If you calculate the total energy, square of the field, square of the electric field plus magnetic field, according to since there is no phase around it, it goes to zero.
Yeah, we'll come to this point when we will discuss the boundary conditions specifically for okay. In free space, this is moving if the direction of the propagation of wave is in this z direction, and the electric field is moving like this way, the magnetic field is like undulating like this. Okay, so we have collected. It's a very simple equation. The only equation which perhaps is the most influential for the interaction. This is called Lorentz law. If you have charge and we have electric field can interact with charge no matter the charge is at rest or is moving. The moment the charges are moving, the magnetic field can also have influence on the charges. Okay, you can expand it. So we will discuss it now in this. We will expand this discussion to our vacuum devices. So the Lorentz force law can be used in static field or dynamic field, or either of them. And the charges, of course, they use electric, and they have their electric and magnetic field character. And vacuum amplifiers basically manipulate around this equation. So first thing first, let's talk about a case where we have a field that is static in time, and that field is electric field, and we have a charge somewhere, and that charge can experience, it's a very simple equation, that charge can experience an acceleration, a change in velocity in the direction of the electric field. It's a dot product. So the maximum kick will be in the direction of the electric field. Okay. For example, if a charge is moving in upward direction, then the cos of 90 is 0. So okay, because v dot e is cos of the theta. So the change in momentum is basically due to the electric field. This is a very simple equation, and it is basically the foundation of electron guns. Electron guns are used to generate electrons, and they are accelerated through a certain potential. Potential means that you have a distribution of charges, and those charges can establish electric field. And if you release electron, the force on the electrons will cause them to accelerate and to gain momentum. And in fact, this is the principle of electrostatic accelerators, and even this many of the electrostatic devices. Okay, now we go to rather a complicated thing, that we have a magnetic field, and now we have to, if you want to have a flavor of it, the current density should be moving. I mean, the J should be there, not rho. So if you have a charge that is moving and it is subjected to a magnetic field, for example, here I have drawn a solenoid, and this solenoid has a peculiar character that has a magnetic field, North Pole, South Pole, and in the center of this magnet, you have more or less parallel lines of magnetic field. So consider that you have an object. Here I have drawn an array of charges. So the object at the center will face no deflection, okay? Whereas the object or the charge which is at the top of that distribution will face a gyrating motion, and it will have a focus sort of effect, focusing effect. But this is very non-linear device. It means that the motion of the charges are coupled in two directions. If the x is changing, the y is also changing. These are the coupled devices. Okay. So you have a tilting effect. The whole distribution tilts, but it also squeezes. So it's a focusing and rotating effect. Focusing and rotating effect. The solenoids are extensively used in, for example, klystrons. Yeah. So another thing which is very important, I'll come to this point once we have finished with this, and we will be discussing the MATLAB programs. There's a character which is called magnetic rigidity. Magnetic rigidity is basically a character of the charge which is moving, and it is basically the ratio of the momentum to its charge, okay? And rho is the radius of the curvature. We have now seen it that the object will be rotating. It has a certain radius of curvature, but how hard it is to bend or to focus the charge depends on its momentum and, of course, on the charge state. So that's why it is called rigidity, how rigid it is to bend or to focus a certain beam. So the higher the momentum, difficult it is. You have to apply larger amount of magnetic force in order to have this kind of effect. Okay, so let's see if a charge is subjected to it. Another thing which is this is another cartoon. It's similar to what it is, what you have seen in the previous slide. It is basically if I have a solenoid in this direction and I'm looking in from the axial direction, then I will see a circle. But if I go to a different frame of reference, then it will make a cycloid sort of movement. So the movement of the charges, it's true for electrons, it will be a cycloid, but if seen from the axial direction, it will be basically a circle which is making a sort of a cycloid impression in the laboratory frame of reference. Okay, this is physics, so we have to give every corner a touch. Okay, now we come to the point where we have time-varying electromagnetic fields. Okay, consider that we have a charge released in free space, and we have electromagnetic radiations. For example, a radar is bombarding or throwing electromagnetic radiations to a certain object. The electrons in that object will behave. Some sort of behavior will be there. What do you think? What will happen? They will start vibrating. Huh? They will start vibrating, and of course other molecules also. But the vibration will be in the direction up and down, up and down, up and down. Okay, but there's a catch here. What if the electromagnetic radiations are confined in metallic boundaries? Then there's a different case. Nature, Allah subhanahu wa ta'ala, has given every creation mode of survival. Mode of survival is everywhere. For example, if we feel cold, we will like try to squeeze our volume maybe, or wear more insulation. What if I inject this electromagnetic radiations, which has orthogonal electric and magnetic field, in a small box. Small box is a cylinder, metallic cylinder. We call it pillbox. Of course, this is taught in the in very first lectures of electromagnetic theory. This is called a pillbox. Okay, pillbox is a sort of I don't know. It's a cup or something. Can I borrow it? Sorry. If this is a bottle, and I have to fill something in it, it is a metallic boundary. And then the electric and magnetic field will basically reorient themselves. How many of you are fond of music? Perhaps everyone. Have anyone played musical instrument? Okay, I give you, at least we have all heard it. What do you play?
Violin.
Violin, that's excellent. Violin, excellent. It has a cavity. It has strings. And you give it a series of
Modes.
Frequencies, yes. And out of those frequencies, it chooses a certain frequency, a band of frequencies. So the mode of survival of those noises is changed. Those musical sounds basically are the manifestation of the reorientation of the vectors, this mechanical waves in that case, and the things are reoriented. We call it tunes. We call it sur in English. In Urdu. I don't know how to call it in Turkish, but maybe someone can help me. The musical sound. How do you call it in Turkish? Notes. Notes. Yes. Note. So the notes are basically the reoriented form of the vibrations. Okay. But there are other instruments which don't have those cavities. I mean, there is a hole from where you can take the sound out. But for example, drum, it has no hole. If it has a hole, it cannot be a drum. It cannot beat. So can you understand? Can you just think, what is the difference? What is the significant physical difference between those two musical instruments? What size? Yes, size. Of course, the larger sizes usually have low frequencies, and smaller the sizes have higher frequency. For example, the guy.
Can I add something?
Yeah.
I think the term you're talking about is tını. It's the one you perceive, like Turkish term.
Okay.
It's the one you perceive, not
Tını.
it.
Okay. No. Thank you. So the musical instruments are basically the analogy, classical analogy of the accelerating structures. We will call it accelerating structures, the cavities, where the electromagnetic radiations, they reorient their vectors in many forms, depending upon, as Professor has already very highlighted, that it depends on the dimensions of the cavity in which those waves are subjected. Okay. So a certain mode, we call it mode. Physicists don't have those fancy terms, boring people, but we call it modes. A certain mode is that the electric field vector is maximum at the center and there is no magnetic field there. Isn't it marvelous? I just told you that one is the other. Wherever is electric field, time varying, magnetic field should be there. But we have very cleverly reoriented those vectors, and at least in this region, there is absolutely no magnetic field, only electric field. This mode, Dr. Ayub told us, this mode is particularly called transverse magnetic 0-1-0 mode. I will not go into the details of this thing, but it is basically a playground of interest for us. We have to release a charge and it will see only electric field. And as we go in towards the walls of, or towards the circumference of this this cavity, the magnetic field starts rising, and short before the end of this boundary, we have a maximum of magnetic field, and then it starts decreasing again. Of course, there's a full lot of mathematics behind it. I will not go into details. You can always refer to some standard books. I will show some references, by the way, at the end. So if someone is interested, that can be found. So this is a very particular mode, a certain sur, a certain tune, which is suitable for electron interaction studies. Okay. This is a CST simulation. I borrowed it from one of my colleagues' slides. This is basically a cartoon showing in 3 dimensions the electric fields and the magnetic field curled around. The magnetic field is curled, electric field is going straight in this direction, in the propagation direction. Remember that we have to have V dot E. The maximum acceleration can occur only if the theta between the velocity vector and the electric field vector is zero, because of course 0 is maximum. Huh? And the magnetic field is curled. So we don't want magnetic field. Why we don't want magnetic field, by the way? Because it will try to make a cycloid motion, and our electrons or charges will feel undue disturbance, perhaps. Okay? So it's a very clever way of devising instruments. By the way, the guy who plays violin, what is the basic, what is the most suitable instrument that you will use to mimic a human voice? Or someone has sung some very beautiful song. What instrument will you choose to mimic that sound or to copy that sound? Drum, violin, piano, guitar?
Not drum, but I have no idea, actually.
The one which is closer to the dimensions of our cavity, the sound cavity. That is violin. Smaller. So I can show you a video, very nice video. There are some nice musicians who play very finely, and they're marvelous. One who loves music can easily understand this thing, by the way. Okay, so not all fields are varying with constant rates. Sometimes the fields are not very fastly changing. Sometimes they're changing very fastly. Okay. Professor talked to us about the slow wave structures. Slow wave structures have waves where the phases are slowed down, deliberately slowed down. There's a purpose to it. And sometimes you have waves which are very close to the velocity of light. So is the behavior of the charges similar in every case, or there is a distinction? There is a distinction. We call this distinction pseudo-static field. When we say pseudo quasi-static field, then we can apply sort of physics that we just discussed in case of static fields. Okay? So a pseudo-electric field, can you possibly think of that scenario? For example, if we have a cathode, we have an anode, and I apply 4, 7, 10 microsecond pulse. That is usually the time period of a pulse in klystrons. Then for that particular moment, for that particular time, the fields are sort of static. Okay, only the rise and falling edges of the wave or of the pulse are different. We will discuss it. And also, what about the gridded guns? We have heard about the gridded guns. Gridded is sort of gauge. it's sort of a chopping thing. It allows electrons to pass through or charges to pass through for a certain period of time. But it's very close. I will discuss it, by the way, if not today, tomorrow, inshallah. The grid is placed very close to the cathode, and a very short pulse is applied on the grid. That grid basically, it's a sort of traffic signal. It accumulates the charge and let go the charge after a certain time. In way we can control the beam very precisely. But what if? But again, it's a time varying electric field. Again, we call this electric field. We deal this in a quasi-static field. The rule of thumb, or a sort of physicist rule, is that if the dimensions or of the space in which those electric fields and time varying electric fields are applied, if the time of flight, electron of course has a certain time of flight for a certain velocity from one point to the other, if the dimensions of that are lesser as compared to the free time of flight and the corresponding de Broglie wavelength, then we can treat those as quasi-static field. We shall discuss this situation when we talk about the gridded electron guns. Here, okay, in fact, this is the slide. So if we have a very short pulse, and for example, in this case, it's sort of nanoseconds, and it's a very high rep rate. And this is applied here at the gun, at the grid of the gun. This is the source of electrons where the electrons are coming through. This is the focusing electrode. If someone is not familiar, don't worry about it. We will discuss in detail the geometry of it in a very great detail tomorrow. The beam which is coming out of this aperture, the anode, is also has this sort of structure. But here we don't apply the rules of changing electric field. We use it as quasi-static field. Okay. Similarly, if this is of course a triode amplifier, nowadays I don't know if people use it or not, but the grid which is placed here is very close to the emitting surface, the cathode, which is placed at high voltages. But here again, the character can be understood easily by applying the rules of static field. Okay. Now, if we have time varying electric field, it's really now time varying. The quasi is put aside. What will happen? Number one thing, the character of it, the time varying electric field, that they are not conservative fields. Electron or charges, if this is filled with the electromagnetic field, the doors outside, the environment outside has no electric field. If someone or the charge comes through this door, it can gain or lose energy depending upon its phase and interaction with the electric and magnetic field. It can leave and go into the same atmosphere, but still it will have, but again it will have higher higher acceleration energy. So this makes these electromagnetic fields non-conservative. Okay. Consider a region which I showed you in this slide, that we have electron coming from this point and leaving through this door aperture, and only the electric and magnetic field is confined in this environment. What will happen? The source of electrons is of course an electron gun. It enters the cavity, and again it comes from one point to the other, and Maxwell's equations are basically doing the magic which is happening inside those cavities. So for the next few slides, we will going through that mathematics. So please don't sleep. Okay, it's a sort of boring thing, but equally important. Important in a sense that I myself cannot survive without understanding the physical inside of those equations. I will not go into the derivations. You can always find it in the standard textbooks, but a bit of it should be tolerable. Consider that we have magnetic field. So these are the only two equations where we have time varying magnetic field and electric fields. So let's play with it. I have to introduce magnetic field here, and I have to introduce electric field here. I give them a scalar product, add them up, and I have this equation. Let's give it a dissection. Let's give it a flavor. Okay. We will go through this thing in detail. Consider that we have a volume where we have charges, and those charges are actually interacting with the electric field. Remember that we have a volume and we inject our particle at a point where there is only electric field. Okay? So this J is interacting with E field in a volume. And that volume also has, if it has this displacement current, you're familiar with it, and it has a magnetic field, and this is filled with certain thing. We call it the energy inside the cavity. Sorry, I have to borrow it again. This bottle can be considered as a cavity. The water inside is electromagnetic radiation, which has a certain weight. I can give it a like vibration, and it will choose one of its favorite modes depending upon the dimensions of this bottle, and the waves have certain mode. If I release some particles inside it, they will like vibrate or something. So consider this as a volume. The bottle is filled with charges. The bottle has some water waves. What if I feel it from outside? What will I feel on the surface? The surface.
Yeah.
I will feel the sound. Where is the sound coming from? This vector. This is the pointing vector. The energy coming out of the cavity, of the volume. This is the simple thing. Okay. Let's give it another dissection. The charges, sorry, okay. This is even better. The charges have basically have a net energy gain. For example, the particles are moving in and out, and this term is basically the net energy change due to the velocity. W is, I'm representing W as the kinetic energy, velocity being V, and it is leaving the surface, leaving through the surface. That's why it has an integral over the surface. The net energy carried away by electrons leaving the cavity or the volume through the surface, S, and of course the rate of change of the stored energy in RF cavity, that is the volume, as the kinetic energy of electrons. The electrons in the cavity can do two things. Either they can deliver the energy or they can take energy from the cavity. So this term takes care of this thing. And this is the stored energy in the cavity. And this is, of course, the pointing vector. Anyone who has taken the electromagnetic course is familiar with this thing. This is the sound in our case. This is the electromagnetic radiation. Sorry, sir.
Sorry, maybe you pointed out, but how to confine the electromagnetic in those?
Okay, how to confine it? Yeah. I can fit in this room because the dimensions of this room is way bigger than me. Okay, I cannot fit myself inside this bottle unless I have an Aladdin gin. So the rule of the thumb is that you have to design your cavity whose dimensions are at least the one wavelength apart. Okay, so there is a way to inject the electromagnetic radiations. We couple it through waveguides, we couple it through the antennas, and the cavity itself should be of the dimensions of the integral multiple of the lambda, the free space wavelength of the wave. Okay, this is a detailed topic, but yeah, perhaps you can ask my colleague or someone here who are more enlightened. But I have given you the references. Thomas P. Wengler or Lapostal, they are the Bibles of this kind of stuff. Sorry. But the rule of thumb is that the lambda should be taken into account. Okay, the free space wavelength of any wave. Okay, so if I just rearrange it and we discuss it term by term, the first term is the rate of change of the stored energy of the in the volume as kinetic energy of the electrons. This is the net energy of the electrons which are leaving through the surface. This is the electromagnetic stored energy in the volume, and this guy, I have bolded it, is the Poynting vector representing flow of electromagnetic radiations energy per unit area, per unit time from the boundary of the surface S. This equation has all the ingredients that you require if you ever want to invent a vacuum device. Okay? What do you need? This two terms comes from the J. Okay? We need J. We need lots and lots of electrons, the current. Okay? And we need a volume which can store the electromagnetic radiation, and that interaction of electrons with these fields can take place. Only then we can have this vector. This is the vector which you guys want to generate. And I'm sorry to say, perhaps at some point, cook someone. This is the vector.
Kashif, that term equals H.
Yeah.
It's indicates the direction of the wave, moving direction of the wave. So, do you mean that the energy is moving through the surface of the cavity?
Yes, we have to give it aperture. We have to give it a way to escape. I will show in the next slide. We have to go because electromagnetic radiations cannot pass through certain boundaries.
Yeah.
But since we are developing the mathematics, the engineering comes in next step.
So we integrate over the aperture.
Yes.
Is the aperture.
Yes, yeah, that's right. Thank you, sir. Okay, this is the point. So we have charges which are coming through in the volume. They gain the velocity, and their kinetic energy is changed. They are leaving with a different velocity. In this case, they are like slowed down because we have taken a radiation out of them. Okay? In accelerator, it's the inverse. We inject this vector inside, and the net energy is positive. I mean, the electrons or the charges move with the higher energy as compared to the electrons or the charges which are injected. So basically, this is the principle, but only the signs are changed depending upon how this thing is done. Okay, just to simplify things, how much time we have?
5 minutes.
5 minutes. Okay, we can continue it after some break, but just take a look on this. We have a full period. Perhaps you asked something. We have a period, and the wave is lasting for a certain time. What happens when the period is over? The equation which I showed a moment ago is simplified, and the term is the kinetic energy W is, which is inside, goes to 0, and eventually there is no stored energy at the end of the cycle. What is left is only this thing, the velocity and the Poynting vector. Okay. This equation is the foundation of the amplifiers, electron amplifiers. Well, I copied it from some text, but in my opinion, my personal opinion is biased towards this detailed history. But anyways, you guys can choose your physics. Okay, so in any case, the difference between the kinetic energy of electron entering and those are leaving the cavity is represented by this over a period of the whole cycle. And that cycle can actually have a feature that mean energy, the difference of energy, can leave or enter through the cavity. So the moral of the story is that at the expense of the velocity of charges, we can generate electromagnetic radiation. So this is the mathematical background, and it has solved many problems and created a lot of them, which we will discuss later. Thank you very much. And if you have any comment, we can discuss it now, maybe over the tea or. Thank you.